I have the pleasure to introduce our first Murray lecturer this semester, Professor Thomas Reiprich. Thomas got his PhD in Munich together with Hans Bohringer, analyzing a complete sample of galaxy clusters selected in X-ray, where he published a well-known paper on cosmology with X-ray galaxy clusters. Then he moved here in US, in Charlottesville, with characterizing. And in 2004, he moved back in Germany, but this time in Bonn, where he got the Minute, which is a position funded by the German Research Foundation that is given to exceptionally young researchers. And then that position was extended by the German Research Foundation in 2010 for a professorship, always still in Bonn. And he's still professor in Bonn, fully funded now by the university since 2015. He's one of the members of the eROSITA collaboration and the Athena consortium, chair of the Galaxy Cluster working groups. And today I think he's going to tell us what he is doing currently and all the related stuff with the eROSITA and Athena. Thank you.
Thank you very much, Lorenzo. It's really a great honor to be here and being able to give a talk. This morning I actually checked when I was here the first time and gave a talk, and that was actually also the last time I gave a talk here, and it's almost 15 years ago. At that time, we were in Charlottesville, Virginia, and we were on our way to Montreal to get our visas extended. And then my wife was heavily pregnant, and then our car broke down, and then Bill pointed out a mechanic, and then he fixed everything. So we did make it to Montreal and back. But today, I would like to start with an introduction of what galaxy clusters are and what some basic cosmological ideas are, what one can do with clusters in general. I assume there's many experts in the audience, but maybe there's a handful or so that are not experts on that. So in these first 10 minutes, the experts, they have to bear with me and can sit back and relax. But I think it's useful if you all start from the same page also. And then I'll talk about some X-ray selected galaxy clusters and some recent results from them, and then I move on to some predictions for eROSITA and what the status is, and then go even further into the future to Athena. So what's a galaxy cluster? As the name implies, it's a cluster of galaxies. So here's an HST observation of one particular galaxy cluster. So all of those galaxies with that color are part of that cluster. There's also some background galaxies whose images are distorted by the strong gravitational field, or it's not really a strong gravitational field, but there's a lot of mass there. And that's in the optical. And if you point the Chandra space telescope, an X-ray telescope there, that's what you see. And then, of course, usually people think, well, that's these X-ray telescopes with this poor spatial resolution. You just merge everything in one big blob. But of course, you know here that this is not the case. Chandra has a better spatial resolution than most optical ground-based telescopes. So the reason it looks like that is there's hot gas in these galaxy clusters that permeates the entire volume. So the X-ray emission is not limited to individual galaxies, but it just fills the entire gravitational potential. So in X-rays, you see the cluster as one object, while in the optical, basically, you see it as a collection of individual objects. You also see a couple of individual objects here. For instance, you see some X-ray emission over there, and that comes from a supermassive black hole that is currently accreting matter in the center of that galaxy. But most of the X-ray emission comes just from gas that is between galaxies. So it's mostly thermal bremsstrahlung from optically thin gas, and it's mostly the electrons that radiate. And these electrons you can also see in a very different wavelength range, in the millimeter, sub-millimeter wavelength range through the so-called Sunyaev-Zeldovich effect. And here's an image taken with the Planck satellite. And overlaid are the X-ray surface brightness contours from ROSAT. And one can see both of them trace the same electron population very well. Not exactly, because the emission does depend differently on the density and the temperature. But in principle, you see basically the same electrons. Okay, here's another image of another famous galaxy cluster, the Perseus cluster, and you can see it at the very center here. And one can see there's maybe something strange going on with that galaxy, some H-alpha filaments. But what is really going on, you can only see when you actually look in X-rays, because that's where the action is. You see these emission from the jets from the supermassive black hole blowing holes into the X-ray emitting gas over here. So that in the optical you just look through all of that gas, you don't see that. Another example, one of the most nearby galaxy clusters, the Virgo galaxy cluster. Optical image again looks like a very boring galaxy except for this jet coming out. And then again, if you look in X-rays or even actually radio emission, you really see where the action is going on. A few more examples how where you can see that the synergy between the X-ray and the radio observations. Here in blue, you see the X-ray emission, and then the radio jets you can see create these cavities, and some more examples over here. And up to now, we were looking basically at the very centers of clusters, but you can also look at the clusters at some larger scale, and also there we have a very nice complementarity between the radio and X-ray observations. Here in blue, you see the X-ray emission of that particular merging galaxy cluster, merging like in this direction. And in red, you can see the radio emission. And these are so-called radio relics, and they are supposed to trace the shock fronts that are moving in this and in this direction. You can also see a couple of AGN that are these sources, but since the relative velocity between the X-ray emitting gas and these galaxies is very large, you don't see the jets like this, but the jets are bent like this. And as you can see, they are all bent in the same direction as one might expect. Okay, then the last wavelength range that is missing in this overview of clusters, the gamma rays. And unfortunately, currently there's not much action going on there. It's hard to see the expected diffuse gamma ray emission from clusters up to now, but at some point it will be detected. Okay, so that was some very basic introduction to clusters, and now a probably even more basic introduction to cosmology. For most of the cosmological tests that people apply, you can classify them into two to three different categories. One is the geometric tests, and that involves distances and volumes. And on the other hand, tests that are based on the growth of structure in the universe. Now, the good thing is, when we will talk about the cluster mass function, which I will do in a minute, it depends on all of those. And that's why clusters are very sensitive to cosmologies. Because these observables, they are related through the redshift, and in particular, that's I think one of two slides where I have some equations on. It's related to the so-called E of z. And so E of z depends on all of these cosmological parameters. For us, important is this omega matter over here, which is the mean normalized matter density in the universe. And let's say dark energy density, and this equation of state of dark energy W over here. And that E of z basically parameterizes the redshift evolution of the Hubble parameter. And the distances are related to that R of z over here, and that depends on that Hubble parameter, so on that E, and on the redshift, of course. And the growth of structure, simply speaking, depends on that growth factor over here, and there's also that E and the H in there. So basically, observationally, you can determine this and the redshift, and then you can constrain all of these parameters that enter here. I will skip the 3.5 kV line where you actually don't need any of this, but I assume you're all aware of this, so I'm not going to say anything about it. So visually, how does it look like? So first of all, the distances in cosmology are not, there's different kinds of distance definitions. For instance, there's the luminosity distance and the angular diameter distance, and they are not the same. And that is because the universe is expanding. And the angular diameter distance actually decreases with increasing redshift, so the distances get smaller again. But the more important point is these distances, they differ depending on what you assume for the cosmological parameter values. So if you change the equation of state like this, then you get these different distances. And similarly with the growth of structure is the growth factor. For different values of cosmological parameters, you get different values as a function of redshift. For instance, for a very high density universe, omega matter 1.0, you go from, let's say, redshift 2 to 0, you go that large a range, while if you have a low value for the omega matter, you go less. And that means there's more growth of structure with higher omega matter, which is not surprising. If you have more mass in the universe, more matter, you also have more growth of structure because of gravity. So what's then the effect of that growth factor on the cluster mass function? So first I should explain what is the cluster mass function. That's just the number density of clusters as a function of mass. So how many galaxy clusters do you have in a given volume, let's say a cubic megaparsec, at a given cluster mass? So for instance 10 to the 15 solar masses or so. And then if you plot that for 3 different redshifts, low redshift here, redshift 0.5, redshift 1 over here, you can see that the evolution differs, again, depending on what the equation of state parameter is. Or it also depends on other cosmological parameters, of course. So if you populate that with data points, you can constrain the equation of state of dark energy, for example. If you only have a local redshift, a local cluster sample, all at low redshift, you can't really constrain the dark energy properties, but you can still constrain some other important cosmological parameters. One is omega matter again, and the other is sigma 8. So what is sigma 8? Sigma 8, so omega matter is the mean normalized matter density, while sigma 8 is a parameter that describes the amplitude of the fluctuations in the matter density in the universe. So the more matter you have, the more growth of structure, the more clusters, the more fluctuations you have, the more clusters you have. So they are, to keep the same number of clusters, basically they are anti-correlated. If your omega matter goes up, sigma 8 needs to go down. However, they are not exactly degenerate, and therefore when you use the shape of the cluster mass function, you can constrain these two individually as well. Okay, so that's for the introduction. Now let's look at some results. And very briefly, I'll talk about some of Gerrit's results, but I assume many of you are already aware of that, so I will keep it very short. So he used the 60 brightest clusters in the sky, brightest in X-rays, and used Chandra observations for all of them, and there's about 100 kiloseconds on average for every of those clusters. And given that these are the brightest clusters, there's enough photons to do the studies as detailed as possible. So skipping all of these, let's say, innovations that Gary did and just focusing on the results, here's the result. Here's sigma 8, and that is omega matter. The constraints from that cluster mass function he constructed are given by that gray contour over here. He also got constraints from the so-called gas mass fraction. There, the basic assumption is that the matter distribution in clusters is the same as the matter distribution in the rest of the universe. And then if you determine the matter distribution in clusters, you can also infer the value of omega matter and independently of sigma 8. So that's those constraints. So if you combine these two, you get the blue ones, which are fairly tight. Then you can compare that to the cosmological constraints that come from the primary anisotropies in the cosmic microwave background, here in this case from the WMAP, 9-year results. And the cluster results are somewhat lower sigma 8 or so, but basically consistent within the 1 sigma regions. Not quite as consistent if you were to put the Planck results here, which would lie over there. But anyway, with the WMAP results, you can combine them, and then you can get these very tiny error ellipse. And these results are also consistent with some of the recent cosmic shear results, as one can see over there. So the summary is, even though the sample has only 60 clusters, because of these very well or very good observations, we can get fairly tight constraints on omega matter and sigma 8. We could probably get even tighter constraints if we trusted the results for galaxy groups more. If we could trust the groups more, then I think we could also get some good constraints on the neutrino masses and also on the theoretically predicted cluster mass function. But what's going on with the groups? So here's the abstract from Garrett's paper, and there's this one sentence here that says, we find that galaxy groups introduce a strong bias since their number density seems to be over-predicted by the halo mass function. So that's one possible explanation. There's a couple of others. Another explanation, as you can read further in later sections in Garrett's paper, a further possibility is that the parent samples where these 60 clusters are taken from are maybe more incomplete at the galaxy group scale than at the galaxy cluster scale. So more incomplete than estimated. Why would that be? The clusters are selected mostly from the ROSAT All-Sky Survey, and most of the cluster surveys on the ROSAT All-Sky Survey were done with a sliding cell box detect source detection algorithm, which is optimized for point sources. If you have a very extended nearby source, that algorithm might miss some of those groups. Now, well, if we say that, then maybe we should also check whether that's actually true. So we reanalyzed the ROSAT All-Sky Survey with a source detection algorithm that is optimized for very extended sources. And when I say we, the primary person doing that is Wei Shu. But before touching the ROSAT All-Sky Survey, she did lots of simulations, so that's also all simulated data. What is shown is two parameters. That's the extent of the detected sources, and that's the extension likelihood of the sources. So how likely is it that the source is more extended than the point spread function? And then all of these data points are simulated AGN, and then we also simulated a couple of clusters with different fluxes and different core radii. And then we decided we are not interested in all of these sources that are close to point sources. We don't need a complete sample. We only want to check whether any clusters or groups have been missed over here. So we decided to put these cuts over here based on the simulations. So then the very same software was run on the real data on the ROSAT All-Sky Survey, and this is how it looks like. And at first I was extremely surprised to see how similar these AGN distributions actually look. That was probably the most interesting result. No. What you can also see, there's some clusters here. They don't have the same distribution as those here, but that doesn't matter at all. Because as I said here, we just picked some fluxes and some core radii, some extensions. So we don't expect to reproduce those exactly over here. Anyway, so that's about 1,000 candidates. And now what is the red and the blue symbols? The red and the blue symbols are those clusters that are already known as X-ray clusters or as Planck-Sunyaev-Zeldovich detected clusters. So the next thing to notice is then that basically almost all our candidates down here, they are already known. So that's good. That means our algorithm works. But one can also see there's this extension here to the very large extent for the sources, where very few are known. So then the question is, what is this? Is this just the extension from the AGN part, or is it just noise, or what is it? So then we try to scrutinize those a little further. And what, of course, helps is optical data to identify the sources. And as it turns out, I'm going to show a couple of examples, several of those are actually nearby galaxy groups. Here's one example, box length is 20 arc minutes, so clear cluster over here. Another example, the contours is from the X-rays. Here's a Sloan Digital Sky Survey image, and here's an Atlas image. That's one of the rare regions where these two optical surveys overlap. And one can see they have roughly similar quality. Probably the seeing is somewhat better for the Atlas. So this source is also, of course, not known as an X-ray cluster or a Z cluster, but it's already known as an Abell cluster. So it's not really a new. It would be surprising if, let's say, these here were actually missed in the past. But anyway, another example. So here I also showed the photon distribution from the ROSAT All-Sky Survey. So we have some idea how many photons go in to the detection and how they are distributed. And again, you can see there's a very clear cluster over here. Another example, an Abell cluster over here, and a Abell cluster over here. No Abell cluster over here, but clearly there is this extended emission detected. Okay, I think one more example, and then we move to something slightly different. Again, no Abell cluster over here, and a very extended distribution of the X-ray photons. Again, that's 1 degree over here. So that is interesting, but in principle we would like to go one step further and only look at those candidates that weren't even detected as an AGN, so no X-ray source at all. So not only not an X-ray cluster, but also not any X-ray source detected in the ROSAT All-Sky Survey. For instance, in the ROSAT faint source catalog. So and there's a couple of those examples where basically no X-ray source was found before, and you can see the photon distribution here, clear cluster. Another example, so there are some regions on the sky where there's no Sloan data, and where we actually only have the old DSS plates, but again, a clear cluster over here, and a very extended distribution. Oh, and that it's pretty hard to see the DSS image, but luckily for that one, we also have an Atlas image, and again, there is this cluster over here. Okay, so in summary, there are several groups and clusters that were missed in the past, and it's not only that they have just a very low flux, that they are just not included in the previous catalogs. Some of them, they were just not found because of the source detection algorithm. Now the question is that enough to actually make any effect when you do the cosmology with the clusters? That we don't know yet, but we are about to check that. But we can, in principle, quantify what the effect might be. And actually, Gerrit already did that in his paper. So what he did is he assumed there's an incompleteness of 25 or 50% at the galaxy group scale, and then checked if one took that into account, how would the constraints on sigma 8 and omega matter change. So here's the default results for the full sample, including all the groups. And then if you, with these two assumptions, basically you move towards the higher omega matter values. And that's not surprising if you remember this one. So here's again the cluster mass function as a function of mass. So the groups are somewhat over here. So if you actually have more groups, then the mass function gets steeper. And for the steeper mass function, you have the higher omega matter values. So that's exactly what you would expect. Okay, so let's move to some other test that we did recently with a cluster sample. And for that, let's take one step back. So that's the other slide with an equation on it. So what's one of the primary foundations of cosmology is the cosmological principle, which states that for us, the universe looks isotropic, which means that in every direction it should look the same, at least at large scales. In principle, that should also hold true for every other co-moving observer, but it should definitely also hold true for us. And with that assumption, plus general relativity, the Friedmann equations follow, and these are these two very simple equations, and they are the basis to calculate everything, basically the density evolution of the universe for the different components, the scale factor evolution, everything is, this is the basis for all of these calculations, and the equations are so simple, at least illustratively, you could derive them in a few lines here on the blackboard. Not strictly speaking, but that's what it is. So some people think it's maybe actually too simple, the equations. But anyway, that is the basis, and the basic assumption is that the universe is isotropic, and that has been with us for 100 years, and of course, for decades, people have checked whether the universe is really isotropic. So we thought, well, let's check it another time. But since we only can work with clusters, we have to think of a test that one can apply with galaxy clusters. So it's actually not very hard to come up with a test using galaxy clusters. And the basic test is to use the so-called luminosity-temperature relation. What's the luminosity-temperature relation? The clusters, the basic property of clusters is their mass, the total mass, including dark matter. And the more massive a cluster is, the bigger it is, the more luminous it is, the higher the temperature of the gas in it. So they are all correlated. Also, the luminosity of a cluster is correlated with the temperature of a cluster. So that relation has been determined also for decades already. So we thought we'd take some large cluster samples and check whether that relation looks the same in all directions in the sky. So why, one more sentence on the LT relation, why the LT relation? The temperature is determined independently of the values of cosmological parameters. But the luminosity obviously not, because you need the luminosity distance. So if there's any anisotropy in the luminosity distance across the sky, it should show up over here. It does turn out that it's actually not so easy to find large cluster samples that are complete and well characterized with temperature measurements. So we actually ended up using one very old from Don Horner's PhD thesis, an ASCA sample, and one from an XM Newton serendipitous survey, XCS survey. And I should point out, this work has been led by Kostas Mikas. Okay, so what's the result? We quantify the result in terms of the normalization of the luminosity-temperature relation, normalization in the luminosity direction, and then show it as a function of galactic longitude. So we have this stripe, and only use those clusters in that longitude range to determine that normalization, and that's the result for the ASCA sample. This sharp jump here is caused by just one outlier. And of course, all these data points are strongly correlated because the areas overlap. So that's one sample, and there's a 3 sigma deviation, but, well, one could say, well, we don't really expect to be it perfectly. But then we have this other sample, and there's only 3 clusters in common between these two samples. So they are completely independent. And the very same pattern shows up there, which is unexpected, because we would like to see the same luminosity-temperature relation in all directions of the sky. Since the luminosity distance is involved, you can also translate that into some relative difference between omega matter values. You can see here in that region of the sky, one would determine a higher value for omega matter, and in that region of the sky, a lower value. Or you can also express it in terms of the Hubble constant, and that is shown over here. So in that particular region of the sky, you would rather determine a higher value of the Hubble constant, even going up to almost 80, and in other regions, a much lower value. So Kostas did check many possible systematic uncertainties, but we didn't really come up with any that could explain that. On the other hand, it would indeed be very surprising if that indeed was some anisotropy in the sky of that magnitude. So currently the status is there's 2 times 3 sigma result, but we would of course like to check that with larger sample and in particular with better characterized samples. And one example would be EE, high flux, and the other example would be eROSITA. So let's skip this. So let's move to eROSITA. That's a German X-ray telescope in a collaboration with Russia, who provide another instrument, the ART-XC, over here. And they also provide the navigator platform and provide the launcher, proton rocket with another upper stage over here. So eROSITA is a new X-ray telescope, and actually it's 7 X-ray telescopes with basically epic PN CCDs at the focus of each of those telescopes, so similar to the XMM Newton ones, and it'll be launched officially end of this year, but realistically probably rather March 2019 into a Lagrange point 2 orbit. And the major science driver is the study of clusters and to use them to study dark energy. And it would have been nice to show that eROSITA has taken off, but this is only on its flight to Moscow. Here's a picture that Peter Predel, the PI of the instrument from MPE, sent me a few days ago. So that was taken in December last year. So that's at the Lavochkin company, I think. And that's eROSITA, ART-XC, and several people working there. So hopefully it's going to be launched in a year or so from now. Now what will we get from it in terms of galaxy clusters? About 100,000 galaxy clusters are expected to be found all over the sky. And the distribution of those clusters is shown over here. So here's the redshift. So redshift 0.1 is here, redshift 1 is here. And here, that axis is the mass. So galaxy groups down here, massive clusters up here. So what's the color? The color is the number of galaxy clusters expected to be detected in each of those bins with eROSITA. And that's the logarithmic color scale. So that color means 100 clusters, let's say here or so. One can see that most of the clusters are around redshift 0.3, 0.4, and with masses of about 10 to the 14 solar masses. Now, that's of course predictions. Some cosmological parameters have been assumed over here, and that landscape changes when you change the values of cosmological parameters, and that's where the sensitivity comes from. Okay. These are detections, but the eROSITA survey data will directly allow us to measure the temperature of clusters for a subset, a small subset of clusters. But small still means about 2,000 galaxy clusters, so significantly larger than the samples that we used up to now. And that will be useful for several purposes, including also doing this anisotropy test again. What are the expected results on cosmological constraints? So maybe just look at this one here first, omega matter, sigma 8. The open ellipses are all fairly recent results from existing cluster samples, and the blue ones are the predictions for eROSITA. So the good thing is, yes, the expected results are tighter than the existing results, but also the shape is interesting because I said earlier there's this anti-correlation between sigma 8 and omega matter. So why are these constraints from these other cluster sample perpendicular to what is expected? That is because they already include WMAP or Planck primary CMB constraints. The eROSITA constraints, even when combined with Planck, still are looking in this direction. That means there's really strong constraints coming from the clusters. And that's the results from Gerrit that I showed earlier. There will also be useful constraints on the equation of state of dark energy. Also, if the sum of the neutrino masses is reasonably large, we might hope to actually measure the neutrino mass with these galaxy clusters. If it's close to the, let's say, lower limit of 0.06, then we will still get some useful upper limits. Okay, so let's move a little more quickly now. That's the cosmology with eROSITA, but we will also be able to do studies of individual clusters with eROSITA. And what's the advantage of eROSITA compared to the other existing telescopes? It's, of course, the large field of view and the grasp. So in the last, 10 years or so, the study of the outskirts of galaxy clusters has been picking up. So with Chandra and XMM, that's a simulation. And what is shown is the gas density, I believe. We are basically limited to that range over here because the particle background of Chandra and XMM Newton is kind of high. With Suzaku, one can hope to go a little bit further out, but there's lots of interesting physics going on over here. So we would like to work more on this. And the other limitation is, of course, if you go to very nearby clusters, then the field of view of Chandra and XMM is just too small to do much. Now, before actually starting the survey, eROSITA will have some fairly short, but still there is one performance verification phase observations of 3 weeks or so. And one of the things that will be observed is that system here. I saw Scott nodding his head. He knows that system. So here's the 2 ROSAT PSPC pointings of that system. So the one cluster is here, and it's actually 2 clusters if you look carefully, and another cluster over here, and there's some indication of some bridge of emission connecting the 2. In white is actually the overlaid Zunya-Zeldovich effect signal, and that is shown as an image over here. So actually very similar structures seen in both of them. Here's a Suzaku observation. The backdrop here is the ROSAT All-Sky observation. And here's the fields of view of Suzaku. And you can see, it's unfortunately tiny fields of view. And here's the corresponding observations. There's also some Chandra observations that Scott showed at the last snow cluster meeting. And I grabbed that image from there, from his talk there. And again, you can see there is some indication of some emission, and I think that might be identified with some galaxy group or so. But again, it would be much nicer to really have a large field of view. And so we proposed, and it got accepted, some so-called raster scan observation of that system. So that's 3 degrees over here, and that's the expected footprint that we would get. And the important thing is not only that these systems are here, but we have enough regions where we can characterize the background or the foreground actually very well. And so we would hope to get some very good constraints on the emission between there, and with the assumptions that we put in, we could also spectrally determine the properties of the filamentary emission, not only the cluster outskirts emission. Okay. Then that's what was the PV phase, but with the survey, survey data, we can also hope to look at some very extended structures in the sky. And one of the biggest cluster in the sky is, of course, the Virgo cluster. You remember this picture here, but that's, of course, the very center of the Virgo cluster. I don't know if that's the right scale here, but it's kind of very small inner part that we are looking at. So that's a ROSAT All-Sky Survey image, and here's M86, known to many people, other known groups down here. So people have, of course, been trying, because the cluster outskirts have become very interesting, have been trying to just add many XMM Newton or Chandra observations in certain areas over here to characterize these parts over here. So some existing XMM observations, and people also invested lots of Suzaku time. So each of them is one Suzaku pointing, and so well, you can estimate how much time it took to make that little stripy image over here. Wouldn't it be great to have basically one image with the XMM Newton spatial resolution and with the Suzaku background? And that's a simulation of what we hope eROSITA would show after the 4-year survey is done. And we estimate that we would have up to 1 million counts from the Virgo cluster if we add up everything in that region over here. Soft proton flares have not been incorporated here in that calculation, so we will have to see. Exposure map is supposed to, in that area, to be fairly homogeneous and flat. Good. The last part, before concluding, is Athena. So Athena is the next large ESA space mission after the next Jupiter mission, which is JUICE, and before the next gravitational wave mission, which is LISA. And it'll do observations, let's say, in the early 2030s or so. That has become somewhat unrealistic, unfortunately, that launch date. So galaxy clusters are one important aspect for the key science of Athena. And of course, black holes is an important aspect. And among the cluster topics, there's one topic we are going to show a few slides, which is the very high redshift galaxy groups. So the very first galaxy groups that start to exist at high redshift, so above redshift 2 or redshift approaching redshift 3. So people study the first stars in the universe, the highest redshift gamma ray bursts, highest redshift galaxies, quasars, and so on. So with Athena, we would like to find the very first galaxy groups in the universe. Okay, so there's 2 detectors on board Athena, supposedly. One is the XIFU, which is very good for spectral resolution, and there's a wide field imager, and that is composed of 4 quadrants of depth FETs over here. Unfortunately, with some gap in between, how large or big that gap is not completely determined yet. But it's a large field of view, it's 40 arc minutes. Not quite as large as eROSITA, but still very large compared to Chandra, for instance. Okay, let's zoom in. And in these kind of forecast simulations, you can not only forecast how the images look like, but for each source you also input a spectrum, so you can really analyze the data in the same way as one would analyze the real data. And to get rid of these gaps, we assumed some Lissajous Dither pattern, and I forgot to mention the main work here is done by Jolie Zhang. Okay, so if one assumes that, an observation might look like this. So you can still see where the gaps are, but there's no region without exposure. But still, unfortunately, here in the very center, we have the best point spread function and the lowest stray light and the best or lowest vignetting. There's, of course, the region with the lowest exposure as well. But it's not that large a region. Okay, and then there's simulated galaxy groups put in here with that mass, 5 times 10 to the 13 solar masses, redshift 1. And for all of these groups, we also put in X-ray AGN at the very center, because at higher redshift we expect it's more likely that there's X-ray AGNs in these groups, which makes it harder to detect these sources as extended, obviously. Okay, so here's the wavelet filtered image and the groups that were detected. And in this case, all of them are detected because it's not that high a redshift. At least, well, in the future, this is not a very high redshift. Currently, that is still very reasonably high redshift for clusters. So let's move a little further, redshift 2.5. Here's the input distribution of these groups. I should point out, in reality, there's many fewer such groups at that high redshift with that mass in a single field of view. And then one sees not every of these groups is detected, but still a significant fraction of those are detected. And here's the distribution. If you do that for different setups, here's the redshift, here's the off-axis angle, and in this diagram here, that number gives you the detection probability of these groups. So again, here redshift 2.5, you still have a reasonable detection probability of almost 50% or so. And I should probably point out that is assuming an 80 kilosecond observation. Now, if you fold that with the cluster mass function, when you know how many of these groups are there, and then fold that with the expected observations that Athena will carry out with the wide field imager, it'll do a survey of several tens of square degrees, then what one finds is that at least 10 groups above redshift 2, above that mass with a gas temperature measurement, will be discovered in the first 4 years. And that assumes let's say, the smaller mirror, which is likely to become the default mirror. So that's a very nice prospect. If you want to know more about Athena, there's this conference coming up in that nice Mediterranean Italian island of Sicily at the end of summer. And yeah, you're all, of course, invited to attend that conference. So to summarize, after the introduction, I talked about some of the current results from existing cluster samples, and then gave some outlook on eROSITA and Athena. And I would like to thank you very much.
Thanks for the nice and clear talk. We have time for questions.
Can you go back to your mass redshift plot for detection with eROSITA?
Yes.
More like a curiosity. That's the flux limit cut, right? On the right there. Yeah.
Indeed.
And there is the effective area of the telescope?
That's well spotted. So it's actually worth and instructive to understand these blue corners here. So the redshift is down here. That means the volume is smallest here, and the massive clusters are rarest, so there's very few of those. Here the volume is actually largest, but since the massive clusters only start to exist late, they haven't formed yet. Now the question here, you are at low redshift, so you should detect also the very low mass groups, and indeed eROSITA will detect them. That's an artificial cut through a redshift dependent count rate limit, because for the cosmology we don't want to use the 10 to the 13 solar mass groups. And it's not a sharp cut, because it's not a sharp mass cut, because there's scatter in the luminosity mass relation. So that's an artificial cut.
One, just an advertisement. So Gabby Alvarez, who worked with me, just submitted a paper on the 3391
okay.
system. So
Yeah, it would be
should be
nice to look at that.
Yeah, right, in the near future. Secondly, I'm just wondering about the anisotropy. So if you had the galactic absorption wrong, that could bias, you end up in a situation with your low mass systems where you can trade off metallicity for temperature, basically, in your fit. So have you looked to see if there's a metallicity anisotropy also?
No, we haven't. I think for the XCS sample, I don't think there's metallicity available. For the ASCA sample, there are. And we haven't looked at that. Costas did look in detail into the NH issue. And there's the first NH issue. When you get it wrong, you might get these systematic effects. There's more subtle effects as well. The first thing that you notice is that in Don Horner's thesis, despite the fact that he says the luminosities are corrected for NH, they're actually not. And so Costas did apply that NH correction, and he also, let's say, applied a total NH correction, like for the molecular hydrogen that is missed by the 21 centimeter observations. And you can't get rid of the effect. And secondly, also in the different regions, you have similar kinds of NH distributions. But I think it might be worth looking into the metallicities to see.
So just to follow on that, you are comparing the normalization of the T relation. Does it mean that you are keeping frozen the slope, or the devices they generate,
Yes.
and then you can have effect.
That is correct. So of course, Costas did try to put the pivot point somewhere in the middle of the sample so that the degeneracy between the slope and the normalization is not that strong, but it's still there. So indeed, for that, we fixed the slopes.
So the way to understand or to improve upon the anisotropy measurement is to go deeper in the same directions and see if the anisotropy still holds. Or real anisotropy would have to go through the whole depth of the universe, right? Not just be a local clumping of material.
Right, it depends what it is. And I think the next step is to have larger samples with better temperature data and a better control of the selection effects. So, for instance, for the ASCA sample, it's just archival sample and nobody knows how they were selected. One thing that Costas did is to check whether maybe there's a higher fraction of clusters that are in superclusters, which might have a different LT relation because it's a denser environment. But it's not the case. He did find that the normalization of clusters in superclusters differs from the normalization of clusters in the field, which is not unexpected, but actually hasn't really been shown by anyone very clearly. But he did find it. So I think the way to go is to have a clearly defined sample with more clusters and better temperature data.
Well, so I got two quick questions. One, early on in the talk, you mentioned that eROSITA was going to basically fly PN sensors. I thought that it was the same technology, but they were actually much better.
Yes, they are.
The energy resolution, in particular at low energies, was actually much better than XMPN. Is that the case?
That is the case. Thanks for pointing it out. I didn't say much about the detectors.
That should be very helpful, for example, for resolving background and.
So there's a couple of significant improvements. So the first is indeed the energy resolution. I'm trying to remember the full width half maximum at half keV, and I think it's maybe 70 eV or something. So that is better than Chandra XMM or Suzaku, and that is very useful for obviously for the low temperature gas. There's another improvement. Of course, you know all the out of time events in the XM epic PN. And that is because there is no frame store CCD, and eROSITA will have that frame store CCD. The other thing it will have a graded Z shield, so we should have very few of the instrumental fluorescent lines. Yeah, so it's better.
In many ways, it seems like. My other question is, in the Virgo survey that you talked about, how far out are you going to actually be able to see? Are you going to actually be able to get to zero radius and beyond in the survey, or is that going to require some type of pointed follow-up later on?
So that's exactly the simulation, and now I realize I forgot to mention his name. So this work is being done by Antonio. By Antonio Perez, and right here. He hasn't gotten to the point yet to analyze that simulation to see, let's say, out to which radius and how large you need to make the annuli or sectors or what to get some useful estimate. What you might be interested to know is what is the typical exposure time in that area. And that will not be very large. It will be 2 kiloseconds or something. So it's clear if you are going to see anything, it will have to be large regions.
It's some large annuli or something.
Yes. But that's exactly the goal of his work to find that out.
Okay.
So while you have this up, are you seeing background here, or are these mostly source counts?
This is basically taking the ROSAT image as an input image and exactly using it as is to show how eROSITA would see it, plus adding the particle background that is expected for eROSITA.
But a million counts over a million pixels is not a lot.
Well,
Yes.
does it include the particle background so much? It doesn't include the sky background?
It's the ROSAT image.
Oh, so it's goodbye. It will include the sky background.
Yes.
Okay.
So it doesn't, this image doesn't, it's big, but it actually hasn't gone, I mean, that's M86, M84 in the corner, right?
Yes.
So
4472 down there.
4472 is further down.
And 49 might be
Right.
this one.
So zero radius is a little bit, I think, beyond that, or close to that. So it's not much beyond the virial radius yet.
Right, it's just what he simulated.
Yeah.
This is probably what the shape of the ROSAT tile is. He probably just took that tile as input.
Did I understand you correctly to argue that one of the selling points of Athena is to find 10 clusters at a redshift greater than 2.5?
It's one out of many. And what I didn't say is Athena will not only be reasonably good in finding these, the limiting factor, I also didn't say that, the limiting factor is just the area that is being surveyed. It's only a couple of tenths of square degrees. If one decided maybe later on in the mission, after the nominal 4 years, to have a larger survey, many more would be found. But let's assume through some other means these groups are being found, for instance with the upcoming SZ instruments. Athena will be very good to follow them up, and probably then with the XI view to get redshifts on the one hand, but also then metallicities and maybe even motions in these very high redshift groups. So it's not only good to discover them, and I agree the selling point would not be with 10. It used to be 25 with the bigger mirror, now it's 10. But it's one of the science objectives.
SPT has already found 3 at redshift above 2.5.
Yeah. Right. Yes. And there's going to
Many
be
more to come.
Yeah. Indeed, we had a meeting in January in the CESTO and Athena meeting of the working group 1, and I did discuss a bit with Michael McDonald, and he showed these plots, and then yes, we are checking what exactly the predictions are, what the time scales are, and then whether or not these science objective might have to be modified or not, we will have to see.
Other questions?
I can't see behind me. If they don't have a question, if I have a question.
Go ahead.
So going back all the way toward the beginning, you had your graph of extent versus the probability of extent.
Yes.
And it actually had structure to it.
Oh, okay.
Right? I mean, it wasn't just...
Yes.
Yeah. So, but the next one.
Yes.
So, you know,
I don't know. Maybe just
yeah, so on the right. So, you know, it has almost two pieces that come out. One piece on the top one. So, what is the origin of the, you know, almost the cavity in the middle? Yeah, why does that live there?
I don't know. I hope it's not that this is just the extension from that AGN branch and that most of these are AGN. I hope that's not the reason. Well, let me explain one more difference between the simulations and the actual data. The simulations actually assume the same exposure everywhere, while the ROSAT All-Sky Survey, of course, has an exposure distribution, and so possibly some of these sources here come in regions where you have maybe a kilosecond or so the longer part.
So that you could know the answer to that question, right? That
Yes.
you could know what the exposure is as a function of,
Yes,
of position.
and simulate it, yes. But it hasn't been done. We didn't do it.
So you didn't do that?
No,
You won't
no,
do
no,
that?
no, no,
But
no.
you might do that, or you don't care?
Well, we have been wondering about that. So I said that's what I not hope is going to be the case. So we were optimistic, assuming that we indeed find this distribution of, let's say, missed groups over here. So that's why currently we are looking in the optical observations of all of these sources and understand what they are. I think we should just do the simulations also with a longer exposure time, so it's not a big deal. And then we would see if something comes up here or not.
Okay, but there's in the black points in the top right, there's 150, 75 sources. One could look and see what their mean exposure is.
I see. Right, and
You
that
could-
you might even have actually done.
So you could know.
I think I remember vaguely that several months ago we looked at the plot extent versus exposure time, whether there was any correlation, but I forget how it looked
Okay.
like.
So can I ask one more question? So if you go even further back to when you're doing mass functions, any of the slides will do. So what are the systematics that are left in here, as far as, the absolute temperature calibrations, calibration versus lensing masses? What is left here, that has an important uncertainty that you'll need to deal with as you get more, as the sample gets larger?
Yes, very good question. As you can imagine, Gary did check for how the results would change if instead of using Chandra, he had used X and emitting. And the change there would be within the statistical uncertainty. Now, obviously, one of the critical issues is what is the mass? For the mass function, you need to know the mass accurately. Accurately means you don't want to have any strong bias, like systematically getting the mass wrong. One plot that illustrates what happens when you get the mass wrong, and in this case it's for eROSITA predictions. Let's assume you get the mass on average wrong by 5%, and then look at the constraints of omega matter and sigma 8. This is if you didn't have any bias, and this is if you had that bias by 5%. So that means that best fit value would be probably somewhere around here, is at the 2 sigma order. So for eROSITA, that we will need to know the masses on average to better than 5%.
So this is the 2,000,
No, that's the 100,000.
100,000 objects. Okay.
So the temperature information is actually ignored here. So we actually know more than what is shown.
So are there plans to be able to get better than 5%?
Yes. So the good thing is the German part of the eROSITA survey is mostly in the southern hemisphere, so in the western galactic half, and there's very good optical data. There's the DES for once, 5,000 square degrees. And there's other surveys, the decals, which one would hope would also be useful to get useful average weak lensing masses for these clusters. On the other hand, also weak lensing can have biases. It's not that, let's say, once you do weak lensing, you don't have any biases anymore. So it's going to be hard work, but we are obviously very aware.
So eventually you'll also have Euclid, for example.
That's right. That's right. Hopefully much later than, but still, after the 4-year eROSITA survey, one might hope that Euclid might just get launched or something. That's true. So that would be another 10,000 square degrees, and I'm not exactly sure where they would go.
Think about, yeah.
On the other hand, very eventually, I would also hope that the scientists in Russia and Germany just collaborate and analyze the full sky together.
But more won't, once you're at your systematic, more won't necessarily just be better.
That's
You're
true.
really going to have to worry about, this absolute calibration.
Yes. Not necessarily. If you calibrate, let's say, if you ignore the temperature information, which is done here, and if you calibrate the masses on the fluxes that you measure with eROSITA, it doesn't matter if the fluxes are off by 50%, as long as they are consistently off. So you determine an eROSITA flux mass relation. Then the calibration cancels out.
And you're just comparing you compare as a function of redshift. Now I'm done.
One very last question. Okay, let's thank Thomas again.
at some point, you're actually fitting on the shape of the mass versus no